and I'm going to tell you a little bit about side channels and how classical side channels are still a problem these days, and what are potential new approaches. I don't know if they work yet, but maybe they work. I have a gut feeling they might work, but can be done about them. So we'll first do a little walkthrough through classic side channels to get you an idea of what is actually happening, what is actually at the moment done to thwart them, and what can possibly be done. So let's start with the side channels. We start from the very beginning and then dig down deeper and deeper and deeper every slide. What is a side channel at all? I don't know if you have any idea about classical side channels. So just for the intuition, a good example is the wastewater analysis during the COVID pandemic, right? We just monitor the water, the sewages, and from that deter there's COVID infections. This is really a side channel. Or different example, from these old CRT screens, you might know them. You could extract the whole screen from a neighboring room just by analyzing the rays of heating radiators. I haven't found the reference, so maybe it's just a good story, but that's also using the heating radiator as a side channel. Or other popular example, very recent, to reconstruct passwords during Zoom calls, just by observing the people typing, or by applying machine learning to detect how different the key sounds and make a model of that, and then you can infer password, or at least narrow them down reasonably. Again, here is the typing or the noise is the side channel. What are the culprits in modern computers that actually cause this side channel? So we don't have any sewage water in computer systems, even though sometimes we might feel like it. But we have stuff like speculative execution. So modern CPUs speculate execution to optimize the control flow, because it's working. It needs to wait for some data, so it just makes assumption and guesses and does error correction if it's wrong way later. So things happen speculatively and leave traces in the CPU caches. Also, there's out-of-order execution happening. Well, if there's a lot of speculation ongoing, then the CPU is free to reorder instructions in whatever manner, such that it's more optimal. As long as the semantics is equivalent, the CPU is free to do this, right? Another famous culprit is hyperthreading. So hyperthreading is a well-known and widely applied technique. That's Intel terminology, AMD terminology, or generic terminology would be symmetric multithreading. It's basically one CPU can classically just execute one program, right? But assembly code, if it gets executed, doesn't make use of all the ALUs in the whole CPU. So the CPU reorders out of order instructions to make use of other parts of the CPU. And basically what the software and the operating system sees is two CPUs, two logical CPUs that are actually just one CPU. So one core usually has two hyperthreads, two threads that appear to be one CPU, but it's just one CPU that's reordering and just using its components optimally to behave like two processors. The bad thing is, all these things are crucial for performance, as in really crucial for performance. Without speculative execution, out-of-order execution, hyperthreading, we would be back in the early 90s. So there's a lot of stuff going on in computers that leave traces, that are potential targets for side channel attacks. But we really need them, because otherwise modern computers wouldn't perform and we wouldn't be where we are now. There's one different distinction. So all these things, that's also part of my research, but I'm not going to talk about this. Side channels does not necessarily mean transient execution attack. Meltdown, Spectre, Riddle, MDS, and friends. transient execution attacks make use of side channels and make use of covered channels based on side channels, but it's not necessarily the same thing. So these class of attacks, I'm not going to talk about it. It's not frequently they're referred to as side channels, but there are transient execution attacks that leverage side channels. So I'm not going to talk about this today. Well, as I just said, transient execution attacks are a big scope of attacks in our own class that uses side channels and covered channels. Actually, it uses covered channels via side channels. Already said that before. But all these terms are very frequently used interchangeably. Even in the Melton and Spector paper, they said side channel in the beginning, and the first thing that the reviewers wrote is, no, that's a covered channel. Please distinguish. Don't ask how I know, but I'm not on the author list or anything. I just happen to know this. So a side channel is really the example that I had before, observing the rays of radiators, observing the sewage for COVID viruses, or just classic power analysis. Just observing something that is a side effect of the execution and draw conclusions from that. And the covered channel is something active, where you use something actively to detect, to extract data. So that the classic basic example is a Trojan horse program. That's something that's sneakily gets installed and sends data in a, hopefully for the author, hidden manner. So it tries to be covered, but it's active, it's transferring. And from side channels, especially if they happen in CPUs, if you tickle CPUs a little bit, you can observe the caching behavior, observe the timing behavior, and create from these differences in the timing offsets in the caching behavior a covered channel to extract data. So you actually use a side channel to create a covered channel. How did this all start? There's a very famous paper from Daniel Bernstein that showed cache time attacks, the first practical paper of a cache time, maybe not the first one, but a very early one, of cache timing attacks on the AES encryption algorithm. So I just here show the abstract. It's it requires known plain text, so that's already a really big limitation. So nothing to panic, because if you have really crucial data, I mean, in the metadata, there might also always be some known plain text, but it's already a big constraint. But back in 2005, it worked over the network on another computer. And it's just blamed on the AES design, on the way that AES behaves, and the way the AES algorithm leaves traces in the machine. But and it's important to mention, it's not on the particular AES libraries. There is no programming error in the library. It's just the side effects of the algorithm. That doesn't mean that AES is a weak or insecure algorithm. It just needs to be implemented in a way that it's sane and that it's safe. Why am I saying this? I'm kind of contradicting myself, because it says it's not to be blamed on the library. Well, if you do a textbook implementation of AES and you don't consider this, then you're vulnerable to side channels. So the textbook implementation per se is not secure. It needs to be needs a more extended way of definition to not depend on the input. We will dig into this a little bit deeper in a few slides, but for now the lesson is AES is secure. The definition of AES really is secure, but it depends on the way it's implemented. And back in 2005, when it was implemented correctly, it was still vulnerable because it was implemented without side channels in mind. Nowadays, this is changed. So And the green line here already says it, and we also will dig into this a little bit deeper. It's super difficult, and actually, strictly speaking, even undecidable to write constant time, high-speed AES software. What does constant time mean? We'll get to it. It's a very bad name, but we'll also get into this. So what to do about this? We have the intuition now that we can observe execution behavior to draw conclusions. So in intuition, a cryptographic algorithm runs, and depending on the secret key, the timing behavior is a little bit different, and from that we can draw a conclusion on the secret key. That's the intuition, and therefore we need constant time, because if every instruction is constant and independent of the input, everything happens at constant time, always the same, like a uniform distribution, then there is nothing to be observed. So what are common approaches and state-of-the-art approaches? That's actually a super old slide of mine. I will correct it in the next slide. When I started my PhD, my intuition was, and my feeling was, software can fix these issues. It's a little bit of a hardware limitation, not really a hardware bug. All these side channels, it's just a side effect of execution, and we can write software in a manner that is secure and that is not observable. We just need to write software very carefully, and I think that's possible. But I changed my mind. I no longer believe this, and we will see why. But we can make it very robust and secure, for reasonably secure, but not fully mathematically proven secure, because there is just too many states of execution. Even a cryptographic library that's not so big has so incredibly many states. Think about every if. So I'm actually already talking about my next slide. So let's proceed with the slide. What can you do as ordinary mortal? Well, that's what Intel recommends. Do not write your own cryptographic libraries. That's basically the official recommendation from Intel. So there's not much that you can do as ordinary mortal. The bad news is I'm not a cryptographer. I'm just a stupid computer scientist. But I still see the danger of side channels on cryptographic applications. So what can you do? I'm definitely not in the position to design new cryptographic algorithms. I would totally follow Intel's advice, absolutely. But what can I still do, and what can people still do against this without deep knowledge about the cryptographic algorithm itself? Well, there is constant time programming, and as I mentioned before, this is a super bad name. The name is historic because of this Daniel Bernstein paper before that I showed you, because it extracted the AES key based on the timing behavior. And the first countermeasures back then, in 2005, 20 years ago, was, well, we need to make everything constant time to avoid these side channels and to mitigate them. But timing is not the only culprit here, right? Actually, constant time programming, and I hate the name, means to write the program in a way that every input that is potentially attacker controlled, so basically any input for a cryptographic library, is executed in a way such that it's independent of the input. We will see. We have some graphics what this means actually. But basically, we need to eliminate all the dependencies on the data flow of the call graph, depending on the input, and all the control flow. So through every if, through every load and store, through everything. And I don't know who of you has ever disassembled even a small program. There is a lot of load and store operations in assembly code in the compiled binary. There's many of them. So the best thing we can do at the moment in practice is harden libraries manually. We'll also get into this, but so manually, manual is cumbersome and error prone. You need deep knowledge about the cryptographic algorithm, to keep it performant and to know where the input goes, how the control flow is, how the data flow is, and so on. So a friend of mine, Pietro Barello, I stole his slides with his friendly permissions, implemented Constantine. It's published at NDS, S&P, I forgot what, CCS 2021, I think, which is a push button approach for generating secure code. It's really powerful. So it can even do both SSL. It's an embedded SSL library. Just throw it into Constantine, and it analyzes the whole binary, the whole control flow graph, and creates a binary, a big binary. We'll see why it's so big. That is Constantine, but it's still a little bit limited. Anyhow, this is very impressive. So it has low overhead for an automatic approach, for a not handcrafted approach. I'll show you some numbers later, and it just has 16% overhead for a push button approach, where you just with the idea, so Pietro is also not a cryptographer, just with the idea, yeah, I take all the inputs, analyze the data flow graph, analyze the control flow graph as good as it gets. We will get into this, and generate a binary that is as secure as possible, with all the conclusions that we can draw from the existing analyses. So the security analysis are really strong, and it's also highly compatible. Why highly compatible? I mean, he can really push button generate secure versions of both SSL, which is a real world library. That's actually pretty impressive, and it's an impressive work. And so some more of his slides to give you examples of existing solutions. His examples were so nice that I just stole them. So let's look at the control flow. This is just some if node, so where you have a branch, and then in a normal program you would just, if depending on some value that depends on the input, either go left and have two execution blocks, so basic blocks, or whatever this is, and in the else case just one. And here you see this is clearly could trigger a timing difference, because executing one block is shorter than executing two blocks. That's the intuition. So branch balancing. So for the references, you would need to go to the Constantine paper. I didn't copy them. Sorry for that. But what branch balancing does is it executes a random garbage node here to make it constant time. I mean, the CPU is still free to execute it at whatever speed it wants, but the blocks that are executed do not depend on the input. So all if branches have the same size like the else branches. Everything is constant. It does not depend on the input. That's the whole idea of branch balancing. The thing is, if constructing this is a little bit cumbersome, because it must not interfere or mess around with the program state, and it still needs to be constant time. So you don't still constant time as in not longer as this branch. So we are kind of limited because as another side effect, you spoil all the CPU caches, lose a lot of performance, and so on. Also with garbage here, you might get, depending on what is in the if and the else, get conditions in caches and wherever. It's just very inefficient and cumbersome. A different example is transactional execution. So the intuition is if an attacker extracts the data using timing side channel on CPU caches, well, before critical branches, just flush all the caches or execute them in some secure way, like on another CPU or wherever. But this is also quite tricky, as simply may crash programs. If you execute things on another CPU, you need to synchronize a lot. You might break invariants, have other paths, and so on. You might even need to unroll some loops, depending on in this approach that might not be really intuitive, but loops are very dangerous for the control flow. Why? Because if the loop depends on the input, it's a high dependency on the execution, right? If an attacker can control the input, how often the loop runs, well, there is a timing difference that he or she can leverage, right? So you need to unroll the loops. Unrolling loops in a big complicated loops that depend on input is a tricky thing, and probably and not just probably, but very hard in practice. And if you isolate these things just get tricky. So this paper is also not it's implemented in a way that it works and that it's reasonable to show the idea, but it still may crash the programs. It's just you don't have too much information about the binary, even if you know the source code, if you want to execute it in a strictly enclaved manner. There's also I wanted to talk about this. So there's also other ways you could preload existing information before branches. So existing information, as in information that's necessary for the process of the cryptographic algorithm. You could preload everything such that everything is in the caches and it's guaranteed to be in the caches. But that's against the nature of the CPU, because, like I said before, CPUs speculate, they reorder. So this is also super expensive. There's even an approach to make RAM oblivious, so to move things out from the RAM that it can no longer be cached, and it's not something the computers are really designed for. It's but the summary is all these things have high overhead and do not consider active attackers like Spectre or Meltdown. So really just passive attackers that don't necessarily interfere with the program in any way. That are just other programs running on the same CPU. So the summary of software side channel attacks, to think again, it allows attackers to leak information from by just observing the microarchitectural state, caches, timing, whatever, or even internal data structures in the CPU that might not even be documented. Riddle, the paper I mentioned before, is such an approach where data is leaked through an undocumented buffer. It's called the line fill buffer. Back then it was unknown, and it was just discovered because a former colleague of mine saw, oh, this is a null pointer. Why is it 32? 32 should be somewhere else. So there was something in the CPU that buffered something, and it was not documented in the Intel manuals, but you could leverage it to and tickle it a little bit to actually extract data from other processes. And Riddle still works, so that's a little bit worrying. So yeah, we've been through this point: cache effect, instruction counts. That was basically the branches that I showed before, and the instruction count should be the same, no matter if you could take the if branch or the else branch. Cache effects, flush and reload, prime and probe. These are just the classic approaches to evict code, to evict data from the caches and to draw a conclusion, because obviously you need to make you need to know how is the timing if data is cached, if data is not cached, and measure the timing to see to draw conclusions from this. So if you want to take a deeper look into the basic concepts, how this works, flush and reload, prime and probe, 2 papers, very good. And port contention, again, just caches running full race conditions, just contention in the CPU. And it's not transient execution attacks. Okay, so we talked a little bit about constant time. Now it's time to annoy Peter a little bit and talk about its limitations. It uses 2 things, and it's actually a big achievement, because I don't know if any of you has ever used SVF for static value flow analysis. That's a beast for binary analysis. It basically does points to analysis, analyzes in the binary where could pointers point to, and so on. For function pointers, for indirect calls, for pointers, it's an unsolved problem to make this complete when you just analyze a binary and get all reasonable possible values of a pointer. But this is information that you need if you want to know, and if you want to determine what input triggers which control flow, and what input triggers which data flow. So SVF is absolutely state of the art. It's genius. It's a big achievement, but it's not a fully points to analysis. Is complete points to analysis or even very serious points to analysis is still limited, simply because there is so many different ways and so many different states that a machine has, and so many different ways how a computer program can be executed. So there is also, he also used the FSAN. That's an LLVM extension. The FSAN stands for data flow sanitizer. It's an LLVM pass, and you can compile LLVM with it. It's a little bit tricky to use. And then you can profile, but with it you can profile programs. So you run a small, let's just make it a small program for now. We'll compile it with a data flow analysis, give it some input, and you really see the full call graph with all data in all states. You can get a full graph of the data and how it flows, where it flows, to which if branches, to which branches it goes, and so on. So lots of information, but the FSAN is an LLVM pass. You need to compile the program with it. What does this mean? It's a dynamic analysis. And dynamic analysis means running it at runtime, and therefore it only catches all the cases that are actually triggered while the program is profiled. It's not a universal guarantee. It's a very practical guarantee, but there is no guarantee that there is no other way to execute the program that might get it into different states that are actually vulnerable and to side channels. So dynamic analysis is per se limited conceptually, and static data value flow analysis is also incomplete because of the state explosion. So Constantine is really good, but it might miss some things. That was the motivation between the things that we will talk in a few slides, the crazy stuff that I'm actually doing. But before we bash too much about this, because it's really good work, I want to show you the case study. So of Constantine. So there is Volt SSL, the small encrypted crypto library, also state of the art and industry standard for embedded crypto libraries. And it has 2 versions. You can compile it with side channel protections and without. So without, because sometimes it doesn't fit your threat model, and then you don't need all this constant time stuff. You can just compile it and execute it a little bit faster. And there's a constant time implementation that you can enable, but it's handwritten. So the function cloning is internal details about how constant time works with all its LLVM passes and analysis. It's it's a little bit out of the scope of this talk what this actually does. Basically, it just clones functions to flatten the call graph tree. So because if you have a function and you have branches, function calls another function, and it's just clones functions, but to flatten the graph, to make it easier to traverse and not so many edges. But that's an implementation detail, also very innovative this year, and actually really crazy to implement this in LLVM. I looked at it, so it's a big achievement. I really admire Pietro for doing this. Anyhow, the constant time implementation just have 11.x overhead to the handwritten VUSec implementation. And for a push button approach, that's actually pretty good, because cryptographic code doesn't run so often, I would say, and it required no effort. And I mean, the code that was that's handwritten by VUSec is written by cryptography experts, and this is just a push button approach. And if you really depend on it, a secure implementation push button with 11x overhead just for some algorithms where you need it, and for some libraries you need it, is actually pretty respectable. That's a very good result. And it also shows the push button approach is ready for real world SSL libraries. I mean, he also tried OpenSSL, but OpenSSL is a beast. That's a big, complex monster. There's no way to properly analyze this. It's just state explosion. So, a small summary of the limits of constant time execution. That's actually not called. It's just called constant time execution, but I would call it input independent execution. State of the art is in crypto libraries. It's still handcrafted, therefore it depends on developer knowledge. But it's still, there is performant solutions out there. But we don't really know if these libraries can be in conditions where they still could leak something because it's handwritten, or automatic generation based on the incomplete information that I mentioned before. So what could be an approach to solve this and to show, hey, this piece of code is really behaves independent? Well, we could apply symbolic execution to analyze this. Do you know what symbolic execution is, or shall I briefly explain it? No anger experts here, CTF players, VUSec hackers. Okay, I stole this from here, but this is a very good example, I think. So we have a random function in some program called bomb, which depends on 3 parameters, right? The character, and the character pointer. And I mean, Nikki would expect that I want to go bomb, that I want to explode the bomb, but in this example, it's not the case. So, what are the conditions to find out that you get here and not to boom? Well, the intuition is, well, you want to go here because yeah, 0. You want the boom to be 1. So you need to go into the else branch. So therefore, A at the A area at location J must not be 2022. This is something a symbolic execution engine would find out, a normal one. So it just analyzes this input, this input, this input, tries variables. It really just runs the program symbolically to find out, yeah, we want to go into this branch. We have this. I have the condition here, the assert, it should not go boom. What are the parameters that should go here? Equals 23. That's actually quite simple, because AJ, yeah, here, 23. This must be 23. This must point us to an array at this location. This also AI 23. That's what a symbolic execution engine will do. Don't worry, we go into this in a little bit more detail in a few slides. But there is one piece that's kind of hard to see. If you have AJ at location 23, that's good. But what is the case? And that's hard to find out. What is if I equals J? Then you also go into boom 0. But that's something hard to find because you depend on the pointer. The pointer you don't know where the pointer is in symbolic execution. You can only analyze small parts of the programs, and you need to make a lot of assumptions. Imagine there's a gazillion of functions until you reach there, so you have a lot of assumptions. You still depend on the whole memory. So when you reach this point, this pointer could point to any location in the memory, the whole memory, wherever. It might even be a crooked run of the program, and this pointer is somehow crooked or whatever. We don't know. We need to model the full memory to have a full understanding, and that's a tricky problem. So how does this symbolic execution work? You take pieces of the software, usually the binary. There's also approaches like CLI for LLVM, where you can work on the LLVM IR and so on. So it does not necessarily need to be binary level. I chose symbolic execution for binary level because I want. We also get to this because I want to go to analyze software that's already out there and that's already compiled. Compilers can also change things, but we'll talk about this in a bit. So it's based on SMT solvers. Go back, SMT solvers, classic example, C3, for instance. That's just big software for those of you who don't know, that can solve constraints like mathematical constraints, formulas bigger like this. So basically the conditions here. We give them these two values, some meta information that we collected before, and the SMT solver says you, based on all the variables that we still have, what values here could be this, could be 23. And then just give you a set of constraints for the program from the beginning to the end that you need to input to get to the location that you want. So for this, I mean, it sounds completely impractical if you have lots of variables, lots of ifs, lots of states. So you can't use too many symbolic values. Symbolic value is really just an X, like in secondary school in math. So all these things, if they become symbolic, are just a constraint to the SMT solver. But there's just too many of them, way too many, because you really need to consider any possible state at any location that the program could be in. So there is really a gazillion of these states. It's not feasible to go through all of them. So what do state-of-the-art symbolic execution do? They concretize a lot. Depending on rules that you can define, you always need to write a small program to write your own constraints and to narrow down the search space based on understanding of the program that you're analyzing. But it concretizes as much as possible, and it guesses. It just guesses to get you somewhere. Yeah, we've been through all the possible variables. We've been through the concretization. So again, what does this mean if we want to do it perfectly? Every load and store that the binary does needs to be modeled in some way, right? Every time you read something from memory, you load something from memory, it needs to be analyzed. Hey, what values could that be? In what states could the memory be in? And so on. So symbolic execution is really great for binary analysis. And you can achieve a lot with it, but it's still a little bit limited. Yet another symbolic execution engine. I need to mention it because it's I based my work on it. Is VUSec. It's just binary security. I put the links in. It's also just binary analysis, symbolic execution to find constraints where you get into states that you define before that you don't want, like the boom before. It's written in OCaml. It's super crazy to read, but it's doing quite well, and it's state of the art. And there's a very exciting thing. Why have we been talking so much about side channels before and about constant time? There is VUSec rel. That's a fork of VUSec, or an extension, that does analysis of binaries on the constant time behavior. So it really does the full work, models the full memory, and checks, does this depend on input or does this not depend on input? And I've mentioned before, this is infeasible. This is not working. The search space is so great. Well, it still is, but it's and therefore VUSec rel is a little bit limited just because it fights too many states. But they just used it for really small toy benchmarks and toy programs where it's still feasible, and they found important things out. So they compiled their toy binaries with different compiler versions, with different compilers, and they found out, yeah, depending on the compiler that you use, even carefully crafted constant time code is sometimes reordered and changed by compiler optimizations. And when there is new compiler optimizations going on with a new compiler version, unexpected things might happen. So that's not something, it's again a sign we should really analyze the binaries if we want to be really sure that things are constant time, because compilers just do shenanigans. Sure, you can turn off these, and developer could turn off these optimizations, can take them into account and whatnot. But it's difficult, error-prone, different new compilers, new optimizations. It's not really a solution. Oops. Something here. I just wanted to go swimming. So great work, but very limited. But still great results to show, hey, all the compiler optimizations are actually an issue for our purposes. So, what is my idea? I promised you some more. Don't worry, it's one of the last slides. I promised you some new ideas in the talk, and I have only one slide on that. So we want to model every law and every store of the whole execution, just like VUSec rel. But VUSec rel does it in a naive way. I looked at it, but I was banging my head way too often because it's OCaml, and it's well written, it's cleverly designed, it's reasonable, it makes sense, but it's not really optimized. And for the loads and store, when we keep track of all the states of the program, we could apply some well-known concept from classic operating system textbook, namely paging. We limit the search page by modeling the full memory like an operating system does. And this is ongoing research, and I don't want to go into too many details, but we basically apply optimizations that are used for operating systems, well known there, to minimize the memory that is actually used and allocated by programs for symbolic execution to analyze binaries. And I have code lying around. It's not published yet, but it's quite promising to have be able to at least analyze binaries a little bit bigger than VUSec rel. So yeah, that's probably my 2 cents. And I think my 2 cents to side channel analysis, if it works out, because in research you never know if things work out or not, right? It might be really, really cursed. And that's it. You're redeemed. That's my final slide. So thanks for your attention. You can follow me or my research group here on Twitter, but I think the new Twitter owner is an imbecile, so we are also on Mastodon, and of course you can email me. And now I'm happy to take questions about, for instance, Amsterdam or anything that interests you. Yeah.
I was wondering, like modern CPUs usually have hardware acceleration for cryptographic algorithms. Are they also prone to these side channel attacks, or are they somehow hardened by the CPU manufacturers for that?
Depends on the CPU. But I mean, the hardware acceleration like AS and I or so, yes, they are hardened as far as I know. But even if you defer all the execution of the AES algorithm to the hardware, there's still loads and stores that you need to make use of it. That's so AES in that case is securely implemented, but all the things around might still cause side channels. And there is papers out there where you can still leak even on modern CPUs. The Bernstein one is just a basic concept of, on implementation running on the CPU, not on the hardware accelerated. But also I wouldn't take it for granted that all the execution on any kind of CPU is always super constant time. It might be reasonably constant time, but I mean, if you can trigger the cryptographic code as many times as you want, right? So you have a lot of approaches, and if you just have a reasonable number of runs where there is a timing difference, then you're already good enough, and you're on the same system, or like in the Bernstein paper, even on a remote system. So you have an indefinite number of attempts. If you're attacking, for instance, a server that runs on the same CPU like you, or on the same VM, well, how can you trigger the SSH key to be loaded into the physical cache of the same machine if you run on the same machine? Well, you just you just connect to the SSH server, and it triggers the key to be loaded and compared to the one that you're sending. So, and you can do this if the SSH server is configured a little bit improperly and it doesn't disconnect you and block you or whatnot. You can do this as many times as you want, and as long as you can have some cases where you can trigger a different behavior, then you already won. Any more questions? Yeah.
First, I want to thank you for the awesome talk.
Yeah. Oh, thank you.
It was nice to hear about your work after quite some years. And
there's more.
I will try to make a slide channel attack.
A slide channel?
Fun with fun.
Yeah, I love it.
Just a thought that I had a second ago now. I was curious if it is possible to, thinking back of Constantine, awesome name, by the way.
Also, it's from Sapienza in Rome, so even better, like the Roman Empire.
There's a 11.4 overhead. Is it possible to run, for example, let's say AES on a specific input, and you also execute it 10 times on some other input that you're currently actually don't need? And the question would be, is it possible to hide more or less which program ran again, or maybe you even mix them, so that an attacker could not tell which computation started and when.
Yeah.
Began.
So
and the idea would be to even out any.
Yeah. So if I understand you correctly, you mean why can't you create as much noise as you can to introduce a jitter to make an attacker's measurements as imprecise as possible?
Yeah, or even in this specific case, you produce the noise with the program itself, and you hope that it somewhat averages out on repeated computation.
Yes, that's if you go through in the Constantine paper, there is more references, and they they definitely cover this this case, but creating lots of noises also kind of these this approach if you do it in the binary itself. So it's tricky, and you still don't know. I mean, it's code that's not needed probably, right? What do you do if the compiler, modern compilers are smart? If it removes it or so. I mean, you can, yeah.
This was somehow the let's say the heuristic approach behind my question, that you don't even bother to think about all these things. You just take the handwritten program as it is, and you simply execute it some X amount of time, and to try to hide a single execution time within this entity of several computations.
So you just
I execute AES 10 times. I might have one execution that took 1 second, another execution took 10 seconds, but they, on average, they will even out on 5 seconds, whatever, and it's fine.
I don't think this will work, because the result of the AES computation would be the same in every case, right?
No, not if you run it on 10 different. 9 of them.
On 10 different. So you basically want to create lots of overhead in the caches. Yeah, I mean, you can. You could definitely do this. Create lots of noise, but if you don't want to create too much noise, because that's a real performance killer.
Yes, I agree, but the approach from Constantine would allow us to make 10 computations. Then we have an overhead of times 10, and we would still perform similar like Constantine.
Yeah, but how would you ensure that that the AES computations are so well? You assume a handcrafted, optimized AES implementation, right?
Not necessarily. I just assume some implementation, not necessarily a constant time optimized version, just some.
Okay, then I lost the point. How do you ensure in that case that, I mean, you
I cannot ensure that it will result in a constant.
Yeah.
For sure not, but
you want to create noise.
It's a random approach. You will just more or less the ideas that you hope that you do.
So basically, you try to create 9 random inputs and try to run the whole 10 executions kind of at the same time, so that you could not measure which is the one that's actually on the real input.
Yes, and then you hope that more or less on any selections of 10 inputs, the accumulated runtime is more or less the same.
Yeah, but how would you guarantee that there is no way to leak which run is the real one? Just because the other, I mean, for instance, you could probably try this, but I still see the problem that there might be some way to identify which to leak which one is the real computation, because at the end, eventually, you need to free all the other runs and so on. And so there might also be some side channel for this. And I mean, you have as many attempts as you want. If you manage to leak, and usually you know the source code and even the binaries that are executed, because you're executed on the same machine, or have or know the library versions and so on. So you could even worsen things, maybe, because if you do 10 times every time, well, there is more training data for the timing and for the timing analysis, if the other computations are still valid AES runs. Could be, but okay, let's go back from those slides. Head back to my Amsterdam slides.
I have a more concrete question too. I was wondering how is the constant time in property of programs being evaluated? AES, for example, has a huge input space. For a specific implementation, how do you evaluate to which measure it is really constant time or not?
Well, you run it and you time it basically.
On how many and on what inputs? On random inputs, on some of them, all of them.
Well, depends on the implementation, and in practice you have benchmarks. I can only tell from the VUSec REL paper where they did all these analysis, and they ran their implementation on a big set of more or less generally accepted. So if you go to the VUSec REL GitHub repo, there is a VUSec REL bench, and it contains a big set of benchmarks, some of them bigger, some of them smaller, and they're generally used and generally accepted examples from NIST and whatnot, so from various sources and papers. So usually these things are evaluated using benchmarks that are out there.
I might also have an idea for which benchmarks. Have you ever considered? Have you ever benchmarked any implementation for a constant time? Or?
Yes, I have.
Good.
But what do you mean?
You create compare some benchmarks.
Yeah, that's what constant time also does.
Yeah, not to compare different benchmarks. You mentioned there are these benchmark sets for this. Yeah, I mean, in the constant time paper there and in the VUSec REL paper, there's various benchmarks for this. Mm-hmm. That's just what state-of-the-art papers use. Mm-hmm. And if you go really well, then just WolfSSL with the WolfSSL test suite, because they also have a test suite handcrafted for constant time behavior. And I have to admit, I don't know how they choose this example. That depends too much on the elliptic curves and so on. There I'm out here, and I'm at my Homer-Simpson slide again. Thank you.
Does this make a difference whether you start from a compiled or interpreted language? Or does it all basically point down to the assembler?
It boils down to whatever you execute on the machine. So I agree for JITted and for interpreted, I mean, especially for JITted languages, you might have optimizations going on that cause some kind of jitter depending on the run, because the JIT compiler just does optimizations at runtime and changes things. On the other hand, you could also learn, an attacker could also learn how these how the JIT works and draw conclusions from that, and under which condition it starts optimizing and whatnot, and that also might highly depend on the input. So actually, it doesn't make any difference, because in the from a timing side channel attacker's perspective, the JIT or the interpreter is the same thing as a CPU, right? It's a thing that executes code based on some rules that you can, and another thing that you can leverage, that you can use to leak information from, because it depends on the things and on the data that gets executed. So I don't think there's a difference.
Thank you.
Any more questions?
Okay, then I need a beer.
Yeah, Manuel, thank you very much. Thank you also for coming. We'll bring out some beers if you're thirsty. It's no problem, because we needed some time to cold. Thanks, Manuel, for coming all the way here only for this meetup. We just important.
Thanks for paying the flight.
Yeah, sure, everything. All right. So thanks again for coming, and see you next time at the next meetup.